Okay, this is a recording of the 2-1A homework assignment. I'm going to use the PDF file as much as I can because a lot of it really doesn't require, I don't think, watching the process of it. Okay, we'll see. Okay, first of all, on these first 14, the directions say find the limits by substitution and support with the graphing calculator. So for substitution, we're simply plugging in -4 in for x. That's the first thing we always want to try whenever we're taking a limit. -4 plus 3 is -1. Remember, a negative sign raised to an even power, 1998 is an even number, is +1. Number 10, plug 2 in. If we get a number out, that is the limit. So you get 4 plus 10 plus 6 all over 4. Add that up, you get 20 over 4, which is 5. That easy. Plug it in. What do you get out? This one is a little bit more challenging. You have to know how this integer function works, and we're going to see it a little bit later on in this lesson as well. But when we plug 1/2 into the integer function, this integer function says the output is always going to be the integer that is less than or equal to that number. The closest integer that's less than or equal to it. Well, the closest integer less than or equal to 1/2 is 0. The two in between 1/2 is 0 and 1. We always want the one that's less than the actual number. 14. Substitute, plug 2 in, you get out the square root of 5. Done. And you can check these in your graphing calculator by plugging them in. Okay? On this one, part of the reason that I'm not processing is to write down all of these numbers here. But what I do want to be able to do is show you how to plug this in and use your calculator again. Okay? So essentially what we're doing is we are trying to find out what the limit of this function might be as x approaches 0. If it has a limit, we have to show that as we get closer to 0 from the left, this would be from the left, equals the same number if we get closer to 0 from the right. Okay? So here we're finding the limit as x approaches 0 from the right. Because 0.1, 0.01, 0.00, these numbers are getting closer and closer and closer to 0, but from the right of 0. That's what this plus sign means. It means from the right. Here, this is finding the limit as we approach 0 from the left. These are the output values. I'm going to show you how I got them in my calculator quick. Okay, but you could pause this right now and write down these numbers if you wanted to. But we can see from the output values here that this number is getting closer and closer and closer to -1. This number is getting closer and closer and closer to -1. Since both of these y values are approaching -1, this tells me the limit as x approaches 0 from the right of f of x equals -1. That's how you read this. The limit as x approaches 0 from the left of f of x also equals -1. If the left-hand limit equals the right-hand limit, then that is the limit. So the limit as x approaches 0 of f of x equals -1. The justification for it is always the same. Since the limit as x approaches 0 from the left of f of x equals the limit as x approaches 0 from the right of f of x. Okay? I'm going to take a moment here and show you how I'm getting these values out of the calculator, because this is not an equivalent step. So the table feature does not work as well as simply doing this. If I type x squared minus x over x into my calculator, so I'm going to go alpha y equals 1, or just enter. X squared minus x. I'm going to cursor down over x. Okay? I'm going to cursor to the right. And then I'm going to go second quit to get back to the home screen. And I'm going to call up that y1 function. Here's how I always call up the y1 function, just because I'm used to these keys from the old calculator. Okay? I am going to go vars, stands for variables. Cursor over to y vars. It's a function that I want. It's y1. Vars over to y vars, function y1. And then I can plug in 0.1. And I get out that number, -0.9. And then all I have to do is go second enter to call it back up, and I'm going to go 0, 1. There's that other number. Second enter, 0, 1. Okay? And you can see how those numbers come out. Let's say it's negative. Then I just go second, enter, call it up. I'm going to come back here. Make sure you use your negative key, not your subtraction. Negative 0.1. Close that. Okay? And hit enter. Oops. Had an error here. Probably because I had that extra parenthesis. That's typically the problem. So I'll eliminate that extra parentheses, hit enter. That's how I get negative 1.1. And I'll just show you one more. If I come back here and make it negative 0.1, I get that. So that's how you're going to get those values out from your calculator. And we'll be using our calculator more extensively in this particular chapter. Okay? Let's move on to the next problem. I always want this nice summary statement explaining why you know this is the limit. You're simply saying the limit as x approaches 0 from the left of f of x equals the limit as x approaches 0 from the right of f of x. That's it. This is going to be the exact same process. I'm not going to do the calculator work for you, but you can type this in. Make sure that you are in radian mode. Call up the y1 function at 0.1. You get out this value. You should have all of these digits written down, so that you can see sometimes it actually will approach a particular decimal value. But look at, this is negative 0.54, then negative 0.506, then positive 0.826, and negative point. It does not seem to be zooming in on a particular value. It's not getting closer and closer and closer to 0 necessarily as we go. Here's this here. Okay? So the limit as x approaches c from the left of f of x, okay, does not equal the limit as x approaches c from the right of f of x. We're getting different values. Therefore, this limit does not exist. Okay? Okay, for problem number 22 then, this says explain why substitution does not work to find the limit, and then find the limits if they exist. So let's look at problem number 22 here. If I plug in 0 for x, I get 1 divided by 0. I cannot divide by 0, so it's a division by 0 error. Does this have a limit? We're going to find out. This is one of the rare cases where you get a number over 0 where you could say that it has a limit. We'll talk about this more in section 2. But a quick sketch of this, remembering that this is a volcano. If I plug 1 in for x, I get 1 back out. It approaches the horizontal asymptote y equals 0 this way. It approaches the vertical asymptote of x equals 0 this way. But I jump across this vertical asymptote to start again. It gives this volcano look. And it's if I approach 0 from the left of this function, it goes to infinity. And if I approach 0 from the right, it goes to infinity. So we're actually going to say in section 2 that this does have a limit of infinity. The AP test will let you say either infinity or does not exist, because some textbooks say that you cannot have infinity or negative infinity as a limiting value. But we are going to. Okay? It will be written both, something like this will be written both ways on the AP test. 24. Again, this is a division by 0. We get 0 over 0. But what I want you to recognize right away is 99% of the time that you get 0 over 0, the function does have a limit. 100% of the time, if it's a polynomial, this is a quadratic, over a polynomial, and you get 0 over 0, it will have a limit every single time. So I FOIL this out. Notice I'm keeping my limit notation as I simplify. FOIL this out. 16 plus 8x plus x squared, and then I have to subtract 16. Never cancel terms and factors in the same step. So I cancel the 16s, then I factor out the x, so I can cancel the x out of the bottom. That's what's creating the problem. That's creating the 0 in the denominator. Once I have that x canceled out of the denominator, now I can take the limit by substitution and get a limiting value of 8. You can type this into your calculator. Approach from the left, 0 from the left, approach 0 from the right, and see that it will approach the value of 8. Okay, so all of these can be checked in your calculator. I will probably show you one of these. This one tells you to not even bother trying substitution, but we should always do it. It says find the limit algebraically, confirm graphically. I won't confirm all of them, but I certainly will do this one quickly. First of all, if I plug 2 in here, I get 4 minus 6 plus 2 is 0. I get 4 minus 4 is 0. 99% of the time, if we get 0 over 0, the limit will exist. 100% of the time, if it's a polynomial over a polynomial, that's what we have here. We have a quadratic over a quadratic. Factor the top. This is why we have to be really good at factoring. Two numbers that multiply to be positive 2 add up to be negative 3. T minus 2 and a t minus 1. This factors that's a difference of two perfect squares. T minus 2, t plus 2. We can cancel this common factor of t minus 2, and now we're left with this rational function. And if I plug 2 in for time, 2 minus 1, 2 plus 2 is 1/4. Let's just take a look at this one quickly in the calculator to verify the existence of this limit being 1/4. Okay, we're going to be able to see this one pretty clearly. Okay, we're approaching 2 of this particular function. So if I go to this calculator, I'm going to clear this out so it's not distracting. I'm going to clear this function out by hitting clear. I'm going to go alpha y equals 1. We really need to get used to using that feature on the calculator. It's so much better. X squared minus 3x plus 2 over x squared minus 4. Okay? And remember, if I just do a zoom 6, here's this rational function. It has a vertical asymptote, has a horizontal asymptote at 1. It looks as if x approaches 2. Okay, and we could zoom in on it a little bit more, but it looks like it's got an actual value there. Why is the function undefined there? That's why zoom 4 works much better. Zoom decimal, because each increment is 1/10 of a unit, so you're more likely to fall on this limiting value of 2 here. Look at it, there's a gap in that graph right there. Okay? But if I zoom in, zoom 2, and I just get close to that value there. So I can zoom in graphically, just like we zoomed in on the last couple problems, just by evaluating the function. Now I'm just going to look at it graphically. Notice this goes x equals 2. Look what y is equaling already. But if I hit trace, I actually see when x is right on 2, if it falls on it, it doesn't. Okay? But as I get, look at, as x equals 2, the value doesn't exist. But we can see as we get close to 2 from the right, as we get close to 2 from the left, this value is getting closer and closer and closer to 1/4. You could zoom in again and again and again. It's going to get closer and closer to 1/4. Remember, it's called a removable discontinuity. Removable discontinuities have limits. Okay, so let's come back and do problem number 28 here. This is the one that tends to give students more difficulty because it's not just a simple factor and cancel. We have to do a little bit more algebra on this particular problem. So, first thing we always want to do is plug in 0. I get 1/2 minus 1/2. I get 0 on top over 0. 0 over 0, the vast majority of the time, is going to have a limit. Can we simplify this expression? Yes. I multiplied this first fraction by 2 over 2. I multiply this second fraction by 2 plus x over 2 plus x to get a common denominator of 2 times 2 plus x. Remember, this fraction then is all over x, so I might as well flip this. This is x over 1. Flip, that's 1 over x. That's why this x shows up in the denominator. I distribute. Cancel the terms first. Do not cancel terms and factors in the same step. Write it like this, then cancel the factor. Now that x is canceled from the denominator, I can plug 0 in and find a limiting value of negative 1/4. We need to be prepared for this type of limit as well. Don't expect that it's always just factor and cancel. A lot of times we'll start off with this rational situation like this. And this is going to help us immensely at the end of this chapter when we're doing the definition of the derivative. Okay? Problem number 30. On this one, it says find the limit graphically using your graphing calculator. Confirm algebraically using the sandwich theorem. We will talk about the sandwich theorem a little bit in class. It's one of those topics that a couple years ago I said, well, I've never really seen it on the AP test. Well, it's been on lately. So it's certainly something that we're going to need to talk about. There is an easier way to actually take this limit without using the sandwich theorem. So I'm going to go through this process here because it's a nice algebraic process. I'm not going to put these on the test or quiz right now. There's going to be a rule called L'Hopital's rule that's going to be much better for dealing with these type of trig situations. Okay? And we can use that on the AP test as well. The biggest thing on this particular problem is we need to get the sine of 2x over 2x because that limiting value is defined to be 1. So if I multiply the top and bottom by 2 over 2, I get something that looks like this. And I use my properties of limits to write this as two separate limits. The limit as x approaches 0 of this factor of 2 times the limit as x approaches 0 of this rational situation right here, sine of 2x over 2x. This, by definition, using the squeeze theorem to verify this limit, is defined to be 1. And 2 times 1 is 2. Okay? The algebra here is good. I would not get too worried about this particular situation. As I said, there's going to be an easier way to do it. On this one, I like showing you this one. And notice again, we get 0 over 0. So we try to simplify. A great technique that we use in calculus is actually separating the numerator over the common denominator. Look what that produces for us here. If I take x over x and make this plus sine of x over x, I can take the separate limit. We have a property that says if you're taking the limit of the sum of two functions, you can take the limit of the first function plus the limit of the second function. Cancel the x. I'm taking the limit as x approaches 0 of 1. The limit as x approaches any value of a constant is just that constant. The limit as x approaches 0 of sine of x over x, just like it was here, is defined to be 1. We actually verify that this is 1 using the squeeze theorem. But once we verify it, then we automatically, we assume that this is always 1. Okay? And 1 plus 1 is 2. We will get more into the squeeze theorem later on. However, this is a nice little algebra situation here that you can take a look at. This is a great one to look at in your calculator and actually see that it does approach the value of 2 from the right and from the left. Problem number 34. 34. Again, the key to this one is interesting, is that you have to remember how to factor the difference of two perfect cubes, not two perfect squares. This is x cubed minus 5 cubed. And it's factorable. It's the cube root of the first minus the cube root of the second times the cube root of the first squared plus the cube root of the first times the cube root of the second plus the cube root of the second squared. All over this x minus 5. And we can cancel. If you forget how to do this, do long division or synthetic division to simplify this, to figure out the factorization. So you can always do long division if you need to simplify the difference of two perfect cubes. So you know that technique as well if you forget this formula. Cancel, plug in 5, and we get out 75 for an answer. Okay? Again, this factoring of the sum or difference of two perfect cubes may pop up 3 or 4 times throughout the year, so I think it's important for you to know it, but you have a technique to verify it using either long division, or in this case, we could use synthetic division as well to verify what this other factor is. Okay? All right. In exercise 37 through 40, determine the graph of this function and investigating the left or right hand behavior. Okay? How do we, first of all, graph this integer function? I want to talk to you about that quick right here. Some students call it the step function. It's called the greatest integer function. In your calculator, it is in your calculator. I'll show you where it's in the calculator when we're done looking at this particular function. Okay? But what I want you to know about the integer function is any input that comes in, the output is going to be the integer, closest integer, that's less than or equal to it. So if I plug 0 in, 0 is equal to 0. 0.1, the greatest integer, less than or equal to it. Okay, the closest integer, less than or equal to it, is 0. 0.9, 0. 0.99999 is 0. But as soon as x hits 1, now the output jumps up to 1. 1.999999. The integer that is less than or equal to that number is 1. But as soon as the input becomes 2, it jumps up to 2. All the way up to 2.99999, repeating. Still goes back to 2. So look at, it's a closed circle on the left, open circle on the right. Closed on the left, open on the right. Closed on the left, open on the right. At each integer value, there is a jump discontinuity. And that's why we're going to see this picture somewhat, because it is a great example of a jump continuity that exists within an actual function, an actual defined function. This function is used a lot. So it's one of those things that's glazed over sometimes in pre-calculus, but it has great practical applications in the field of computer science, anytime you're using a rounding subroutine, but also in the world of finance, in billing. So if you use your cell phone for 5 minutes and 3 seconds, you're getting charged for 6 minutes. So it's an adaptation of this because we're going to the greatest integer, not the integer behind, but it's just an adaptation of this function. So dropping off decimal values is something that we do in a lot of practical applications. Let's look from the negative side here. If I plug in negative 0.1, the closest integer less than or equal to it is negative 1. That's why it's negative 1, not 0. All the way back to negative 0.99999, repeating. We'll still go back to negative 1. But then as soon, and even negative 1, the closest integer less than or equal to negative 1 is negative 1. But as soon as we hit negative 1.000001, now it's going to go back to negative 2. So the step looks the same on the negative side. It's a closed circle on the left and an open circle on the right. Okay? So we need to know how this integer function works. Great application in 2 fields that we just talked about, and we should know this step function. We're going to see it again throughout this chapter. So now let's take a look. What is the limit as x approaches 0 from the right? Part of the reason why I'm not sketching this for you, just giving you an example of this because you can pause it, is so when we look at limits, I have this nice little cursor here. If I want to take the limit as x approaches 0 from the right, I start to the right of x being 0. And as I get closer and closer and closer and closer to x being 0, the y value is getting closer and closer and closer to 0. Good? What about the limit as x approaches 0 from the left? Now I've got to start to the left of 0. My y value is negative 1, negative 1, negative 1. It's actually getting closer and closer and closer and closer to negative 1. So the right-hand limit is 0. The left-hand limit is negative 1. Therefore, there is no limit as x approaches 0 of the integer function. As a matter of fact, there is no limit as x approaches any integer value of the integer function because there is a jump discontinuity at every integer value. Okay? What is the limit as x approaches 0.01 of the integer function? Notice there's no plus or minus here. Well, because if I plug in 0.01, I get out 0. And as I approach 0.01 from the left and 0.01 from the right, they're both approaching 0. So even if this is a really small number like this, we can still approach it from the left and from the right, and we're going to approach 0. What is the limit as x approaches 2 from the left? Okay? So x is like 1.5. Here it is. I'm getting out a value of 1. 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 As I approach 2 from the left, the y value is getting closer and closer and closer to 1. Even though the limit as I approach 2 from the right is 2. The left-hand limit does not equal the right-hand limit. There is no limit as x approaches 2 of the integer function. But we can find the left-hand limit and the right-hand limit. So it's a great function to look at to investigate limits. Here's another one. We're going to see this one frequently. We've already talked about this function in Chapter 1. If you understand how to break down absolute value functions, it makes the graph really easy. That's why we worked on breaking these down into their piecewise components. The absolute value of x is going to be, in order to get rid of the bars, if x is less than 0, I have to negate what's inside the absolute value bars. X divided by negative x is negative 1. So if x is already a positive number, so if I plug in 1, 2, 3, I can get rid of the bars and I don't have to negate anything. I can just get rid of the bars. So if x is greater than 0, I get x over x, which is positive 1. Notice this function is not defined at 0. I would have a division by 0 error. But if I graph this function, when x is less than 0, the y value is always negative 1. When x is greater than 0, the y value is always positive 1. So what is the limit as x approaches 0 from the right? Positive 1. What is the limit as x approaches 0 from the left? Negative 1. What is the limit as x approaches 0 of this function? Does not exist. Always verify. If it's a DNE, that's an E there, always verify by saying since the limit as x approaches 0 from the left of this function does not equal the limit as x approaches 0 from the right of this function. Okay? The left-hand limit does not equal the right-hand limit. There is no limit. Notice this is another jump discontinuity. Jump discontinuities do not have limits. Removable discontinuities have limits. Okay? So here it is. And I just restate it again here. Okay? So if you have it up there, that's good enough. All right? But we have to be used to this function now and how to break it into its piecewise components. Okay, this next section right here is my favorite part of this. And you're probably more likely to see these type of questions on the AP test, particularly multiple choice questions, as we go through these next series. And this is where my cursor is going to be very helpful. Okay? So here it is. The limit as x approaches 1 from the right. That's how we read this. Start to the right of 1. As I get closer and closer and closer to 1, the y value is getting closer and closer and closer to 1. Remember, the limiting value is always the y value. So that is true. The limit as x approaches 2 does not exist. Well, as I approach 2 from the left, I get out 1. As I approach 2 from the right, I get out 1. The limit exists. That's false. Okay? It's a false statement. The limit as x approaches 2 does exist. The value is 1. This says the limit as x approaches 2 of f of x equals 2. That's false. It's not 2, it's 1. As I approach from the left and the right, they both approach 1. That's false. F at 2 is 2. But we don't care what the value of the function is at 2 when we're finding the limit. We care what happens as we get really close to 2 from the left and really close to 2 from the right. D, the limit as x approaches 1 from the left is 2. I'm getting closer and closer and closer to 1 from the left. I'm coming from the left. Yeah, that y value is getting closer and closer and closer to 2. The limit as x approaches 1 from the right of f of x equals 1. Here we are. We're to the right of 1. We're getting really, really close to 1. From the right is 1. Okay, let's go back up to this one because I didn't see that negative sign there. I was approaching negative 1 from the right. and that is 1 as well, so that's true. Okay? As we approach 1 from the right, positive 1 from the right is also 1, so that's true. F. The limit as x approaches 1 equals does not exist. That is true. The left-hand limit we said was 2. The right-hand limit we said was 1. If the left-hand limit is not equal to the right-hand limit, then there is no limit. The limit does not exist. G. This says the limit as x approaches 0 from the right equals the limit as x approaches 0 from the left. You can always see it's true, but let's go up and take a look. The limit as x approaches 0 from the right, the y value is getting closer and closer and closer to 0. The limit as x approaches 0 from the left, the y value is getting closer and closer and closer to 0. It's true. The limiting value is 0. Okay? So that's true. These are the two that tend to give students more difficulty than anything. So the limit as x approaches c of this function exists at every c between -1 and 1. Let's go up and look. Between -1 and 1, does the limit exist everywhere? Between -1, not including the endpoints. It had parentheses, not including the endpoints, because the limit clearly does not exist at 1. Okay? But yeah, every interior point here, if I approach from the left and from the right, it's going to approach the same value. It's a nice continuous situation. So that would be true. Yes, it does. Okay? So that's true. But this one here is a little more tricky. The limit as x approaches c of f of x exists at every c in the interval from 1 to 3. In the interval from 1 to 3. Well, we only have one point of discontinuity, and that's at x equals 2. But we already said the limit exists here, because the limit from the left of 2 equals the limit as x approaches 2 from the right. They both equal 1. So the answer here is true. The limit does exist everywhere, even though we have this removable discontinuity. The limit exists at a removable discontinuity. So that is true. The limit exists at every c in that interval. The only point in question is at x equals 2, and we already said that the limit exists there. True. This is the type of question that they do like to put on the AP test, right? It's very thought-provoking. You have to think about the fact that the only point in question is at x equals 2, but the limit does exist there, even though we have a removable discontinuity. All right. Now we have a bunch of these functions. Use the graph to estimate the limits and the value of the function, or explain why the limit does not exist. So anytime the limit does not exist, explain why. And I'm going to explain every time it does exist. Let's take a look. This one might be a little bit hard to tell, but it's a horizontal line right here at 3. This is a horizontal line here at -2. So the limit as x approaches 3 from the left. Here's the left of 3, x equals 3. As x gets closer and closer and closer to 3, it's 2.99999. The y value is still 3. As x gets closer to 3 from the right, it's 3.000001. The y value is -2. Since the left-hand limit does not equal the right-hand limit, there is no limit. It also asks, what is f at 3? F at 3 is 1. But this is still a jump discontinuity. It's not a removable. A removable discontinuity is when you approach the same value from the left and the right, yet there's a hole there. So think of a hole. Okay? This is still a jump discontinuity. But f at 3 is defined to be 1. So the limit does not exist. Our justification is always the same. The limit as x approaches 3 from the left of this function does not equal the limit as x approaches 3 from the right of this function. 46. Now we have a little bit more of a curvature to this function. But start to the left of -4. The limit as x approaches -4 from the left. Get closer and closer and closer to -4 from the left. If I'm looking at -4.00001, the y value is getting closer and closer and closer to +5. The limit as x approaches -4 from the right, -3.99999. the y value is getting closer and closer and closer to 2. Since the left-hand limit does not equal the right-hand limit, there is no limit. The limit does not exist. Even though g at -4 is also 2, it doesn't matter. It doesn't matter. This is a jump discontinuity. Jump discontinuities do not have limits. Justification: the limit as t approaches -4 from the left of g of t does not equal the limit as t approaches -4 from the right of g of t. Always justify when the limit does not exist. This is a jump discontinuity. Not my S there. Discontinuity. 47. Let's take a look at this one. This is a nice continuous situation. The limit as x approaches 0 from the left. Here it is. -0.000001. The y value is getting closer and closer and closer to -4. Approach 0 from the right. The y value is getting closer and closer and closer to -4. What is the limit as h approaches 0 then? -4, because the left-hand limit equals the right-hand limit. What is the value of this function at -4? That's how we're going to guarantee continuity. If we can show that the limit exists and the value of the limit is the same as the value of the function, that's going to guarantee that the function is continuous at that value. Our justification: the limit as x approaches 0 from the left of f of h equals the limit as h approaches 0 from the right of f of h. They both equal -4. There should be -4 here, not 0. Okay? It should be -4. Here's how we explain continuity. F of h is continuous at h equals 0. Since the limit as h approaches 0 from the left of f of h equals the limit as h approaches 0 from the right of f of h equals f at 0. Since they all equal -4, that guarantees continuity. We'll practice this. You don't have to write this down. We're going to practice this in section 3. 48. Here's another picture. The limit as x approaches -2 from the left. Get closer and closer and closer to -2. The y value is getting closer to 3. -2 from the right. Y value is getting closer and closer and closer to +3. Therefore, the limit is 3 because the left-hand limit equals the right-hand limit. So here's my justification. The limit as s approaches -2 from the left of this function equals the limit as x approaches -2 from the right. And since both the left-hand limit and right-hand limit equals the value of the function at -2, that guarantees continuity. Just real quickly, the limit as s approaches 0 from the left here is 0. The limit as x approaches 0 from the right looks like it's going to -infinity. That's why the limit does not exist here, because we have this. It's actually an infinite discontinuity when this goes down like that forever. Okay? The left-hand limit does not equal the right-hand limit. So the limit does not exist at 0, but it does at -2. 49. As we approach 0 from the left, getting closer and closer to 0, the y value is getting closer and closer and closer to +4. The limit as we approach 0 from the right, the y value is getting closer and closer and closer to -3. Even though we have this open circle there, that's okay. Therefore, the limit does not exist because the left-hand limit does not equal the right-hand limit. F at 0 is defined to be 4. It's solid here, open here. It cannot be closed on both, otherwise it's not a function. Okay? So f at 0 is 4. This is another example of a jump discontinuity. 50. Limit as x approaches 2 from the left. The y value is getting closer and closer and closer to 1. As we approach 2 from the right, the y value is getting closer and closer and closer to 1. Therefore, the limiting value is 1. Even though the value of the function at 2 is 3, this point has been removed and placed right here. It's still a removable discontinuity. As we approach from the left and the right, we're approaching this y value of 1. Removable discontinuities, also known as a hole, has a limit, even though it's not continuous there. So, the justification is that the limit as x approaches 2 from the left equals the limit as x approaches 2 from the right. They both equal 1. That's why the limit exists. It's a removable discontinuity because g of x is not continuous at x equals 2 since the limit as x approaches 2 does not equal g at 2. Since these are different, that tells us that the function is not continuous at that point. 56. All right, this is just using those properties of limits, and they do pop up occasionally. This should be pretty straightforward. There's one question like this on the test, but it's pretty easy. We have a property that says if I'm taking the limit as x approaches any value of a sum of two functions, I can just look at it as two separate limits and add those limits together. They tell you the value of the limits right here. So we're just adding 7 plus negative 3 is 4. It also works for multiplication. If I'm taking the limit as x approaches a value of a product of two functions, I can take the limit as x approaches that number of the first function times the limit as x approaches that number of the second function. So I'm just multiplying those two. I have a property involving limits that tells me we can do this. This is the constant multiple rule that says if I take the limit as x approaches a number of a constant times a function, I can pull the constant out front and just take the limit as x approaches that number of the function. They tell me this value is negative 3, so 4 times negative 3 is negative 12. It even works with a quotient. I can take the limit of the top function over the limit of the bottom function, provided that the bottom function does not go to 0. If the limit of the bottom function is 0, then we have problems. Okay? But we get negative 7/3. Those should be pretty straightforward. 58. On problem number 58, you have to draw the function first. And remember I said we're going to have a lot of piecewise functions in this chapter. So 58 and 60, you just have to draw the piecewise function. Start at 2 with an open circle because it's not defined at 2, and then we have a slope of up 1, back 1, up 1, back 1. It's just a line with a slope of negative 1 and a y-intercept of positive 3. Then when x equals 2, we jump up here and we have this little point right here. Now, is this a jump discontinuity or removable? Let's see. When I plug 2 in here, 2 divided by 2 is 1. I'm taking off from the open circle, not the closed circle, or not some other value. I'm taking off from the open circle. Now the slope is up 1 over 2, up 1 over 2, up 1 over 2. Once you have it graphed, what is the limit as x approaches c? Remember, c is 2 in this problem. From the right, we're getting closer and closer and closer to 2 from the right. The y value is getting closer and closer and closer to 1. The limit as x approaches c from the left is also 1. Therefore, the limit as x approaches c is 1, even though f at 2 is 2. We don't care what the value of the function is when we're finding the value of the limit. We care what the value of the function is when we're trying to determine continuity. Okay? This is still called a removable discontinuity. Anytime that the left-hand limit equals the right-hand limit, okay? But that point has been removed. Even if it's removed and placed somewhere else, it's called a removable discontinuity. So the justification is the limit as x approaches 2 from the right of this function equals the limit as x approaches 2 from the left of this function. They both equal 1. That's why the limit exists. However, it is a removable discontinuity since the limit as x approaches 2 from, the limit as x approaches 2, we already said was 1, does not equal f at 2. This is 1. The limiting value is 1. The value of the function is 2. Since they are not equal, we do not have continuity. That's how we're going to verify continuity in section 3. Let's graph this one. This is a lot easier if you recognize that this is an upside down parabola. I have to plug negative 1 in to see where my hole is. I get a hole at 0. I can plug 0 in, get 1 out. I can plug positive 1 in, get 0 out. You can plug in some other numbers and see this parabola that opens downward. Yet, when x equals -1, that point has been removed and placed up here. The limit as x approaches c from the right is 0. The limit as x approaches c from the left is 0. Therefore, the limit as x approaches c is 0. Why? Because the left-hand limit equals the right-hand limit. This is always going to be our justification, and I will ask you to justify it every time on tests and quizzes. This is a removable discontinuity, however, because the limit as x approaches -1 of this function does not equal f at -1. F at -1 has a value of 2, not 0. If we wanted to make this function continuous, I could take this point from here and put it right here. And if I just change that to be 0, this would be a continuous piecewise function. It would fill in the hole created by the first piece. Last part, true or false. The limit as x approaches c from the left of fx equals 2. The limit as x approaches c from the right of fx equals 2. Therefore, the limit as x approaches c of f of x equals 2. True. That's a definition of a limit. If the left-hand limit equals the right-hand limit, that is the limit. 72. Is this limit 2? I verified it for you here algebraically. We actually did the same problem earlier. We separate the numerator over the common denominator. I can look at this as two separate limits because I have a property that says the sum of two functions. I can take the limit of those functions separately and then add them together. But the key is we have to remember that this limit is defined to be 1. And we'll look at this one in class. You'll actually see it. Okay? 1 plus 1 is 2. 73 through 76. We're going to use this picture right here that you have to create, and then we're going to do some multiple choice. Okay? So this is a line. If I plug 1 in, I get 1 out, and it's closed. It's closed. It's got a slope of up 1, back 1, up 1, back 1, up 1, back 1. There's that line. This is also a line, except when I plug 1 in. When I plug 1 in here, I get 1/2 plus 1. I actually get out 3/2, or 1 and 1/2 out. And then I'm going up 1 over 2, up 1 over 2. You can see it coming like this, but this is approaching a value here of 1 and 1/2. 1/2 plus 1 is 1 and 1/2. So what is the value of the limit as x approaches 1 from the left? As we get closer and closer and closer to 1 from the left, the y value is getting closer and closer and closer to 1. What is the value of the limit as x approaches 1 from the right? As 1's getting closer and closer, as x is getting closer and closer and closer to 1 from the right, the y value is getting closer and closer and closer to 1 1/2, or 3/2. What is the value of the limit as x approaches 1 of this function? It does not exist. Here's the justification. Since the limit as x approaches 1 from the left of this function does not equal the limit as x approaches 1 from the right of this function. What is the value of f at 1? Well, f at 1 is defined by this top piece. 2 minus 1 is 1. F at 1 is that solid dot right there. F at 1 is 1. Okay? So that's a nice overview of limits. How do we take a left-hand limit, a right-hand limit? Does the left-hand limit equal the right-hand limit? If they are equal, then that is the limit. But if they are not equal, then the limit does not exist. Good?